I would wait a while, actually.
That too.
So, I need to calculate this term now.
Go, yeah.
Right? And I don't even go through that term in my notes. So I'm just going to state the result here, which is that
L
now
over
we
F
have to
squared?
add to that. We add the term in the 80, which is this, minus acceleration there. No.
Wait, is that a minus or an equal?
There's actually another term.
Is that a minus sign or an equal sign?
That's a minus sign.
Oh.
There is another term. Minus v prime n dot a over c over 1 minus. There we go. That's the completely simplified form. Plus other terms, because I've already reduced it here. And then when I put the lowest order terms together, so once again, I make another level of approximation and only go to the lowest order terms, I end up with that is approximately equal to Q over C squared. And this is the one we're going to keep.
Should that A in the last term be?
Yeah, I have an extra term here that I don't like.
You mean n is n cross n hat minus b prime over c cross a prime?
Yes.
So that isn't actually on dropping order terms. That is just the exact version of that.
That's after I'm done. I just have that one left. But my problem is the definition of n prime. And I don't remember what it is.
Wait, where's n prime?
So I'm going to, what?
Where's n prime?
Oh, it's just n cross n minus b prime over c? Well, n
Cross
cross n
A.
prime is 0.
Cross a prime.
Cross a prime. Yes, good. Okay, good. Then I don't have to have a different n there. That's what I was worried about. I was saying, where is that different n coming from? Minus v prime over c cross a prime over plus other terms, lower order terms.
So that isn't actually, according to the book, that isn't actually dropping any more terms than we already did. That's just identically equal to what you have written there, according to the book.
Well, there's plus terms here. Oh, so you're saying that's just a simplification of that.
The only thing you're missing is the extra parentheses. So the parentheses end on this A. I don't know if that matters.
Oh, a bracket here?
And then from the
But this is already
from the n cross, there's an extra bracket outside your bracket that ends on the A. I don't know if that matters.
that matters. That matters.
Okay.
Thank you. Yeah. I was looking at it and saying I still got a problem because if I do that first, I get 0. Okay, but this works. This is better.
Yeah.
Okay,
Professor,
yes,
should that last A on the bottom have a prime?
yes. All the accelerations are of the charge, the source, right? All right, this is actually correct relativistically. Not correct, it's approximately correct relativistically. Right? If I use V much, much less than C, right, then a lot of these terms drop out. In fact, this term and that term drop out. So for classical, now I have an approximation. I've got Q over C squared N cross N cross A prime divided by R minus R prime. Yes, I like that one. Okay. So this electric field that we observe, we have to be far enough away that we can discard all the 1 over r squared, 1 over r cubed terms. So this is the lowest order term, all right? But if you think about this electric field, I've got a charge over here, an observation point over there, observation point over there, and so this is my vector n, pointing from here to there, so it points that way, okay? If the acceleration is along the direction n between the two charges, I got nothing. I observe nothing there, okay? So the acceleration actually has to have some component that's perpendicular to the direction between the source point and the observation point. I know I said two charges a moment ago, but I meant source point and observation point, right? And the field that I observe out there is going to be at right angles to this and parallel to the acceleration, because I've got an n cross A cross n, right? So I'm going to observe a field out here which points that way, and I'll only observe field perpendicular to the acceleration of the charge, right? So I have a field that goes out that sort of looks like that in terms of its magnitude.
Infinity.
9, 10. That's good. And that's, I've just discussed a charge which is accelerating like so, all right? We can think about a charge moving along some path, all right? And if the charge, let's say, maintains its velocity, well, let me make it go in a circle. So it maintains its speed, rather, but it is accelerating, and the acceleration points that way, right? Then this charge at this instant is going to radiate in that direction. Well, it's going to radiate like so, right? But the strongest radiation will be in the forward direction, right? This idea here, when we get to relativistic speeds, we would say if we went through that, did the first term more carefully as a relativistic correction, we'd find that the field pattern would squish and look forward in the perpendicular to the direction it'll, if we're traveling at relativistic speeds, this looks like this, okay? And so the radiation from the accelerating charge just comes right out in that direction. And that acceleration radiation is called synchrotron radiation for applications. You had a question?
I was going to ask if that was Cherenkov radiation.
It's not Cherenkov, it's synchrotron. Yeah.
Could you be a little more descriptive on your diagram of the electric field lines? Just kind of picture it. And I'm not entirely sure what those lines are.
Oh. Probably, I won't do it today because I have pretty pictures in my notes.
Okay.
And I'll bring my computer next time around and project it.
Okay.
Okay? But the field lines look like dipole fields. They look like this. Let's point that out. All right, let's see, what do I want to say? I did say this already. The electric field drops off as 1 over r. The radiation field drops off as 1 over r. And that's good because we know that intensity drops off as 1 over r squared. And intensity, this is the pointing factor, is field squared. So it all fits together dimensionally. Radiation pattern. I've said that, and I have a picture here, but it's not as good as the picture that I will project next time around. So it's as I said, there are lobes with their max perpendicular to the direction of acceleration. And the pointing vector then looks like this. C over 4 pi, well you do this, p squared is, putting it all together, q squared over 4 pi c cubed, acceleration squared, sine squared theta over r minus r prime squared and hat. So the pointing vector points that way. All right, and it is sine squared of theta. I have to think about, I don't have it. Oh, I do have a drawing of theta. Theta is the angle between the acceleration. Oh, that works out. That's good. The angle between the acceleration and the observation direction. So it maximizes perpendicular to the acceleration. And that is then the pointing vector. The joke is done here, so I can erase that.
Yep.
Okay.
Easter egg.
So that's the dipole radiation pattern. Well, actually, I have the pointing vector, so I can take this another step and work out the power and everything else. So I have a charge which is accelerating with acceleration A. Did this. Leave it here. Be careful, I'll write this as gradient B. No, it's not. That's the whole thing. P. Okay. So I've got my pointing vector. If I want to know the power that's emitting, then the power per unit area is the pointing vector. So I can write this as S dot dA integrated, and well, that would be the power. That's that. In an area of dA, which is S, magnitude of the pointing vector, r minus r prime distance squared d omega. So the power per solid angle is the magnitude of the pointing vector which depends upon angle, all right, times r minus r squared. And finishing plugging that in, it's q squared over 4 pi c squared, a prime squared magnitude, sine squared theta.
What happened to
What I dropped?
The extra c in the bottom of
Here,
yeah? It should just be c cubed.
There should be.
here,
Yeah, it should just be c cubed.
good, thank you. And the total power radiated then by that accelerating charge is going to be, I just integrate that over all angles. And so total power is 2/3 q squared over c squared times the acceleration squared.
It's still c cubed.
So now, we've all learned about, in Physics 1, about harmonic oscillators. So we can ask what's the power radiated by a charge that's just harmonically oscillating. All right. It's got an amplitude of oscillation, which is,
q over c cubed. Q squared.
let's call that D. Let's call that 2D. All right. I'll have a frequency of oscillation of omega. So the acceleration in that case, so for a harmonic oscillator, I have an acceleration which is equal to d omega squared sine function, oscillating function. That's it, right? Oh, no, that's it.
Omega
So for-
squared d.
What?
Omega squared d.
That's just d times omega squared, that's the same thing.
I know. Just
It
moves confusion.
looks like
Oh.
a derivative.
I'll tell you what. Let me make the amplitude Z0. How's that?
Okay.
Okay. And so then, let's see. Yeah, my pointing vector is proportional to the acceleration squared. So it turns out that then my power, my total power, I can get rid of the magic here now too. My total power is 2/3 q squared over c squared
Cubed.
Cubed.
cubed times z0 squared omega to the 4th. So the power coming out of an oscillating charge is proportional to the frequency to the 4th power. You got a question, Jesse? And this should be consistent with what you learned from Rayleigh scattering, for example. All right, I'll talk about scattering next class, I hope. Yes.
So where's that energy coming from that gets radiated?
Oh, you've got to drive the charge.
Okay.
Yeah, yeah. Yeah, there's got to be a source. It would be, and next class I will talk about that. I don't think I want to get into it this class. Let me see. Yeah, on the next page of my notes, I just gave you the relativistic expression, and I'm not going to write it down here. And yeah, I will save that for the next class to talk about sort of the general properties of oscillating sources. But in particular, I'll talk about antennas and driving current in an antenna and the radiation that produces. So that was plenty of material for today. I think I'm going to stop here.